the ultimate mega material. Once the go-to metal for kings and warriors, it now holds up the Golden Gate Bridge, the Sears Tower, and every car on the road. But the secrets of steel might just surprise you. So let's find out now on How Stuff Works. Imagine a world where the tallest habitable buildings top out at just 100 feet, where the longest bridge span is just a few hundred feet long. A world without cars or trains or oil rigs. Can you imagine a world like that? If you did, you've just imagined what the world would be like without steel.
We were able to build longer, stronger bridges, much taller buildings. We were able to build automobiles.
Steel is the super metal that supports our world. Here's something to put our need for steel in perspective. Every single year, the world devours more than 1 billion tons of steel. That's enough to rebuild the Golden Gate Bridge 12,000 times over.
You can shape it, you can form it, you can cut it, you can weld it together. You can build anything that you can think of out of steel.
So what's steel's secret? The perfect blend of two of the most common elements in the Earth's crust, malleable iron and brittle carbon. Depending on how they're mixed, these two basic elements can create a material with incredible properties. Flexible enough to turn into stretchy cable and stiff enough to stop bullets. Steel. It's drawn enemy fire since the first armored tank rolled onto the battlefield during World War I. But that was nearly a century ago. The first steel armor is no longer bulletproof because modern guns are so much more powerful. Today, a .50 caliber round travels more than 4,000 feet per second. It blows holes the size of grapefruits in solid cinder block walls and makes Swiss cheese of older steel armor. And it's not even the deadliest threat troops face.
The war in Afghanistan and Iraq put our fighters right in the middle of an urban situation. Different warfare, different needs. They had to combat different threats. And one of those threats was fragmentation devices.
A standard Humvee is made of steel sheet metal. This kind of steel is fine for everyday use. But just like the doors of your own car, the steel isn't very hard, which means that an IED can rip through the metal, injuring or killing the crew. The US Army had to do something. Luckily, steel was up to the challenge. And amazingly, all it takes to toughen up steel is a blast of heat and a splash of water.
Come on, all fours into two.
The darkest night, our Army came to us and said, hey, we need you guys to get with these scientists and come up with an armor solution so that we can protect our soldiers.
And the way they combated that was with the add-on armor.
Steel armor strong enough to protect soldiers against both .50 caliber fire and IEDs. It's called a gunner protection kit, and it's designed to mount onto a Humvee.
It is made of armor plate along with ballistic glass. It has a battery-powered motorized transversing unit that allows it to rotate 360 degrees around the vehicle.
To the naked eye, this special steel looks identical to the standard stuff, just a bit thicker. But inside, it's a different story. The key to its protective abilities is called grain. Standard steel has pretty big grains, but in the gunner protection kit, the steel has been treated so that the grain of the metal is much more uniform. With the molecules perfectly aligned, it can make this steel virtually impenetrable.
the high quality steel that we make, that we produce. That makes it better out in the field for the soldier.
But how did the Army harden steel into a form capable of defeating the deadliest bullets and bombs? First, it added other metals like nickel and chromium to the iron and carbon in standard steel to create a super hard steel alloy. Then it rolled that steel to create what's called RHA, or rolled homogeneous armor.
This is RHA, and it's super tough.
And how does rolling make steel stronger?
We really stretch them out, and what that does is it provides us a very long grain that has excellent properties, specifically in that direction.
But rolling the steel is just the beginning. Just outside Davenport, Iowa, is the Rock Island Arsenal's 1.5 million square foot manufacturing facility. Here, RHA becomes even stronger. The trick is as simple as a lot of heat and a bunch of cold water. As RHA warms up, its grain structure aligns in a way that produces super strength.
We get a whole new set of grains that have excellent combinations of strength and ductility.
Each sheet bakes for an hour at about 1400 degrees. And amazingly, the heat forces the grain structure inside the RHA to uniformly align, like a billion tiny soldiers all raising their shields at once in exactly the same position.
You can now quench it and temper it, and you can get excellent strength ductility properties that enable it to resist penetration.
Before the uniform grain structure loses any of its newfound strength, the metal is quenched in a bath of cold water. The sudden drop in temperature essentially freezes all those tiny molecular shields in place.
Quenching is the process where you heat it up to this higher temperature. What happens is that the steel changes its structure. So the atoms in the steel arrange themselves in a slightly different way than they are arranged when the steel is just sitting at room temperature.
But that slight difference in the grain is enough to dramatically increase the shield strength. That strength comes at a price though. Now it's too hard to be bent and shaped into finished armor plates. So it's heated a second time, then allowed to cool slowly in a treatment called tempering. What's so amazing is that tempering makes the steel flexible enough to be worked, but keeps the hardness of the heat treating.
Tempering is very useful. What you really want to do is you want to make sure that you have some toughness, ability to absorb energy left in that material. You do that by raising the temperature up.
Something made of a less strong material won't stand up to the punishment that our equipment is expected to receive in the different environments our soldiers serve.
So the RHA is ready to protect troops in battle. But how can these straight plates form a round gunner protection kit?
If you bend a solid piece, it retains its structural integrity.
State-of-the-art brake presses at Rock Island Arsenal make bending the tough 3/8-inch hardened steel look as easy as folding paper. But don't let appearances fool you. This steel is so tough that without these powerful machines, shaping it would be all but impossible.
It'd take an army of guys with sledgehammers, and I don't think you'd ever get the job done.
Since American forces began employing the new hardened steel alloy in 2004, Humvee gunner-related deaths and injuries from IEDs and explosions have dropped dramatically.
The soldiers send us pictures and thank yous all the time. They've shown us plenty of vehicles that have been blown up, and then they send a script along with it that says, thank you, all of us walked away from this.
The stuff we make here goes directly into the fight, and it makes a difference so that our sons and daughters can come back safely. That's kind of my bumper sticker.
The blast crew will put about 2,000 pounds of powder in each hole, and that's roughly equivalent to, in each hole, what they set up off in Oklahoma City at the bombing there.
Our shelter is 1,000 feet away. That's the safe limit for us. All other personnel has to be 2,000 feet away from the blast zone.
The charges these men are setting cover more than an acre of ground and pack half the explosive force of the first atomic bomb. But why would someone risk his life just for some dirt? The answer is that this isn't any old dirt. This is taconite, the raw material that will one day become the world's original supermetal, steel. About 98% of steel is iron. The problem is that because iron atoms like to bond with oxygen atoms, it's tough to find iron in its pure state. Instead, iron is found mixed in with a bunch of different minerals, like in the flint-like sediment called taconite. These layers of compressed sediment are only about 25% iron oxide, mixed with silica and other impurities. That means it takes at least 4 pounds of ore to make a single pound of metal. In fact, 50 years ago, this low-grade taconite was considered a waste product, not a source of ore.
Around World War II, we ran out of magnetite, and what's commonly used now is taconite. And it's a high-effort, low-reward ore, but it's pretty much all we have now.
In the mountains of northern Minnesota, ArcelorMittal operates one of the world's largest iron ore mines. In the blink of an eye, over 300,000 tons of rock shoot skyward.
Yeah, you can feel the ground shake miles away, and you can hear it miles away.
Because so much ore is needed to make steel, everything works on a mind-boggling scale. The crude ore is snapped up in buckets big enough to hold a car and dumped into trucks the size of houses.
We're going down into the bottom of the pit to load LC ore from the crusher. Should be right around 200 tons, give or take.
Their goal? To transform these rocks that are about 25% iron into a concentrated 62% iron pellet. At that concentration, it can be usefully smelted. But first, you have to get rid of everything else. Step 1 is to crush the chunks of taconite.
You virtually have to beat the iron ore out of the taconite to obtain anything usable.
Operating like a 900 horsepower mortar and pestle, the primary crusher busts boulders at a rate of 3,000 tons an hour. Then 800-pound steel rods pulverize it into the consistency of sand. But why all the pounding? The answer is that it makes it possible to use iron's secret ability to separate it from all the other junk. Magnetism.
Magnetism is actually an element of the electromagnetic force, which is actually quite a bit stronger than gravity. A bar magnet like this one, there are electrons in here, and each electron is itself a little tiny magnet.
You know, if you superimpose a magnetic coil around them, all of a sudden you get one electron spinning, the other one that was going randomly, all of a sudden it's going successfully together.
And that lets giant magnets suck the iron particles away from the waste minerals, because only iron is attracted to the magnetic force.
The nifty thing is when we are going to ores like taconite that is very high silica content, we break up the particles. One way of easily extracting that is actually to use magnetic separators.
Of course, this still isn't pure iron. Most of the other impurities have been crushed and sifted away. But there's still one left: oxygen. And breaking that bond is one of the greatest challenges in modern industry. The final step of stripping the oxygen won't happen here, though. Instead, this material has to head to a foundry. To get it ready to travel, the 65% pure iron ore is mixed with an adhesive and formed into pellets. But ironically, these iron ore pellets are too soft to travel. So first, they're baked like little metallic cookies.
They're 9.5% moisture yet, and they're very fragile, so they have to be dried in the furnace and fired at high temperature to give them their strength.
The result, pellets capable of withstanding 600 pounds of pressure.
The pellets from here are shipped by rail and boat down to the blast furnace, and from that are made into steel.
This is the ideal pellet, 3/8 by 1/2 inch in size, made in Minnesota.
So 8,000 tons of pellets at a time, more than 900,000 tons a day, are shipped to waiting barges on Lake Superior. From there, they head to foundries to be transformed into steel.
It's a never-ending job. You can't keep up.
But they won't be able to keep up forever. Most experts estimate that the U.S. has just 27 billion more tons of usefully extractable iron ore. After that, it's all gone. The Golden Gate Bridge, the George Washington Bridge, towering monuments of American engineering that soar over dizzying expanses. Combined, they stretch more than 7,700 feet across open space. These are spans that would have been impossible to cross if it weren't for steel.
It's a key component in the bridge construction process.
Of course, everyone knows steel can bear a heavy load.
This steel is what supports the superstructure. You know, it just wouldn't work without the steel.
But it's not its load-bearing or compression strength that makes steel a super material of bridge building. It's another kind of strength. One that's found not in the biggest and heaviest slabs of metal, but in the smallest. For thousands of years, anyone wanting to build a bridge had to make a choice: stone or rope.
You want a bridge to appear to you to be rigid, to be able to bear a lot of stresses, and be able to provide a flat surface.
Like steel, stone can support incredible loads, but it's very heavy, stiff, and brittle. Rope made of natural materials is light and stretchy, but not very rigid. To make bridges span greater distances, engineers needed a quantum leap, a material that was both strong and flexible. And with the mass production of steel in the mid-1800s, they got it.
When they develop these steels, all of a sudden when they start comparing them to the properties and performance of wood, rope, other materials, it was just superior.
Because steel wasn't just strong like stone, it turned out it could also be made flexible like rope.
Ductility is the ability of a material to bend.
That kind of strength is called tensile strength, and steel has lots of it.
We'll make what's called a tensile specimen. So we'll machine the material down here and we'll pull on it. Now the material initially will respond like a rubber band. We'll put a load on it, we take the load off, it goes back. You really want that type of behavior because if you build a bridge out of it, if it sags, you want it to come back.
In fact, a single rope of wire, just 1 inch in diameter, can support more than 50 tons, which makes it ideal for holding up the span of long bridges.
This is the backbone of the bridge. Without steel, the bridge would crumble up and fall, though.
Amazingly, steel's tensile strength is even greater than its compression strength, meaning you can dangle more weight from a steel wire than you could stack on top of a steel girder of equal weight.
But with a bridge strand or a wire rope, you can gain a strength level approximately 3.5 times what you would have with an equivalent amount of plate or I-beam. So you can gain the strength without the mass.
But turning a thick piece of steel into a slender strand of wire is no easy job. It takes some seriously powerful equipment, like the machines here at Wireco in Kansas City, Missouri. In an average shift, the company transforms 123 tons of steel into wire.
We make wire ropes that are as small as, say, a 32nd of an inch diameter, all the way up to 5-inch diameter.
But how do you turn a steel rod that's 11 millimeters thick and 1,000 feet long into a wire that's 80,000 feet long and only 4 millimeters thick? Turns out, it's just like making taffy. You just have to pull a whole lot harder.
Then the strands go immediately into what we call the dies, where the rope is formed. And then from this point on, the double drum capstans are used to pull the material, pull the finished rope through the machine.
It takes more than 11,000 pounds of force to pull one steel rod through the tiny opening in the dies. But as the wire is drawn out, something incredible happens. Unlike materials such as aluminum and plastic, which become weaker as they are stretched thin, steel responds to the stress in the opposite way.
When you draw it and you put preferential stresses in it, that's when you will actually increase the strength and actually improve its ductility and its fatigue resistance.
And this strength can be magnified by weaving the wires together into a single, giant braid of high tensile steel.
Really amazing how they come, you get 30 wires and it comes down here and makes this finished strand comes out here.
It will take 1.7 million pounds to pull that strand in two, to break it.
And that's good news to the guys building a new bridge across the Mississippi near St. Paul, Minnesota.
We have a very long span length here. We have roughly about 500 feet that we're spanning across the river.
Only here, the steel rope isn't used to suspend the deck from above, like in a traditional suspension bridge. Instead, it's woven right through the core of the structure.
This is a major structural component in the bridge. This is a post-tensioning tendon. You can put close to 900,000 pounds of force in the entire tendon.
Once the bridge is complete, these massive steel cables will be cinched down under incredible pressure to keep the bridge tight. Here, steel's ductility and incredible tensile strength will act more like a belt than like suspenders.
The way it works is, the harder you pull on the cable, the more that collar grips the cable.
The result? A new bridge capable of withstanding the weight and punishment delivered by thousands of vehicles per day.
Its ultimate tensile strength is 270,000 pounds per square inch, so it's a very strong material.
We need something that's going to last 100 years.
And in steel wire, they've got it. Making steel in massive quantities was one of the great technological challenges of the Industrial Revolution. But it turns out that the secret to creating this mega material was known as far back as 300 BC, when it was made in India and Sri Lanka. The trick to creating this metal was in getting the exact right combination of steel's two main components, iron and carbon. But today, steel is everywhere. So how did it become the workhorse of the modern world? The answer is Henry Bessemer. Bessemer was a British scientist who in 1856 figured out an efficient way to turn iron and carbon into steel. He did it by using hot blasts of oxygen inside a specialized furnace to reduce the amount of carbon in the metal.
The Bessemer process made steel production far more efficient than it ever had been in history.
If you want to make good, high-quality steel, you blow pure oxygen through the iron, and this oxidizes the carbon that is in the iron.
With temperatures over 2,000 degrees, the oxygen is literally burning the carbon out of the steel. Every day, 17,000 tons of iron ore pours into the furnaces at the ArcelorMittal Steel Mill in Cleveland, Ohio. And each year, this sprawling 1,000-acre facility single-handedly cranks out enough raw steel to build a train track around the globe.
This plant is the most efficient integrated steel plant anywhere in the world.
There's always a hot stove online.
Foundries like this one use extreme heat and heavy machinery to blast away impurities from the iron ore and infuse carbon, creating a metal stronger, more flexible, and less dense than iron. Turning low-grade ore into the most used metal in the world starts at a 200-foot-tall furnace. This is where the iron ore is hit with heat generated by a type of fuel called coke.
Coke is the result of burning the impurities and the junk out of coal that you don't need to get to the good stuff, which is going to burn cleanly and give you the nice, hot, clean fire that you need to make steel.
It's called the blast furnace because as the ore and coke flow downward, they're met by a 1,600-degree blast of hot air moving at 110,000 cubic feet per minute.
The wind is coming in at what we call the Bosch level of the furnace through nozzles, which are called tuyeres, and we have 18 of them depending on the size of the blast furnace. That air is pushing up through a solid burden material.
The superheated air ignites the coke like charcoal in a grill and heats up the furnace to nearly 4,000 degrees Fahrenheit. At this temperature, the oxygen is finally blasted away, leaving pure molten iron. But it's also doing something even more amazing. As the heat from the coke flame strips away the oxygen, the carbon in the coke is bonding to the iron.
You have hot blast going in, you have the material going in at the top of the furnace, and it's melting, and as it's melting, it's going down.
Under the extreme heat, the mixture liquefies. Impurities like silica and sulfur rise to the top. The heavier iron sinks to the bottom, where it's drawn out in a glowing molten stream.
The furnace until it turns into liquid, and it comes out the tap hole.
Every 45 minutes, some 500 tons of molten metal, called pig iron, gushes from the tap. It's called pig iron because it was originally cast into molds resembling piglets suckling a sow. But ironically, though the iron has been freed from the oxygen, the molten pig iron that flows from the furnace has a new problem: too much carbon. Over 4%, which makes the resulting metal much too brittle. To become steel, that number needs to be reduced to less than 2%.
It's all one continuous process.
We want a very specific strength level. We need the carbon in a very critical range.
To get it right, the carbon-loaded pig iron must undergo one final treatment in the oxygen furnace. Inside this iron cask, the molten steel, already at more than 2,000 degrees, is blasted with jets of pure oxygen. The molten steel ignites the oxygen, only this time the fuel isn't coke. It's the actual carbon atoms bonded to the iron. Basically, the molten material itself is burning.
We blow 25,000 cubic feet of oxygen per minute into the bath in the vessel. The oxygen reacts with the carbon and reduces the carbon level.
The longer and hotter it burns, the more the carbon burns away. The molten metal that pours from the chamber is now a perfect blend of soft iron and brittle carbon. A metal that is strong but ductile, hard but malleable, and forms into solid glowing slabs, ready to span rivers and plow through the ocean. This is steel. But the steel is still red hot, with a temperature over 1,000 degrees. So the metal is transferred to a series of casters and rollers, where it's cooled with water and reduced from 75,000-pound 9-inch slabs to a ribbon just 3/4 of an inch thick. The entire furnace process takes just 2.5 hours to turn the natural mined substance of iron ore into the world's most widely used high-strength metal.
We are very proud. Without us, a lot of stuff can't be made.
It's easy to take steel for granted, but the truth is, this incredible material is running out. Elemental iron is only made in the hearts of stars. No new iron is ever created on Earth. But luckily, this mega material has one more trick up its sleeve. It's infinitely recyclable. Steel's two main ingredients, carbon and iron, do not degrade or break down. They are eternal, just waiting to be heated to the right temperature and reform as brand new steel. Amazingly, almost 30% of the steel we use today in our cars, refrigerators, and even warships has already been recycled at least 3 times.
We would have run out of natural resources long ago with steel. You know, the global demands from China, from India, South America, all over. So the recycling is a key aspect.
Of course, just because you don't have to blast recycled steel out of the ground doesn't mean making it is easy. Like mining and smelting, it's hot, it's dirty, and it has its own peculiar dangers. But they're used to that here at Grossman Iron and Steel, where they've been scrapping metal for more than 80 years. The job and hazards begin when independent scrap dealers show up at the yard in St. Louis with their loads.
We get the washers, we get the dryers, we get buses, we get old trailers, tractor trailers. We'll get dump trucks in here. We will get old bicycles, you name it.
The scrap brought in reveals just how much steel we use. But the trick to recycling is to get just the steel. More than 350 fully loaded trucks roll into this sprawling 22-acre facility each day. Most of what they are carrying is metal, but if explosive or radioactive materials slip through, the results could be catastrophic.
Even the small propane bottles like you would use for camping gear or for a propane torch for soldering could cause quite an explosion.
Specialized detectors monitor for radiation. Any item emitting an unacceptable radiation level is immediately barred from the site.
If there is a detection, it stops that entire downstream of conveyor belts in less than 1 second. At that point, everything ceases operation, and we find out what it is and remove it.
But 99% of this scrap is ideal to be transformed back into fresh product to feed global demand.
Someone's old Volkswagen may come in, and when it comes out, we produce the material to maybe bring it back as a Maserati.
Once the scrap is sorted by size, weight, and type, a Caterpillar 345 excavator armed with high-powered shears is unleashed on the mountain of metal. With jaws exerting 1,000 tons of cutting pressure, no other tool can both move and chop this many varieties of scrap steel.
We'll cut it into sections approximately 6 to 10 foot long, and depending on the diameter of it, and that allows it to go through the mill without choking it down.
As 6 perfectly synchronized cranes transfer the metal, 3,300 tons at a time, to a 9-foot wide conveyor belt.
Pipe can be a particular hazardous thing to grab, because if you grab it and you have one loose piece, it's kind of like picking up a handful of sticks.
Its destination, an 8,000 horsepower mega shredder.
I'm the king of destruction for 8 hours.
The shredder is a giant food processor, but instead of a cutting ring, it has 10 800-pound hammers, turning at 450 revolutions per minute.
Whenever that is spinning and the material comes in, we have a force that's equivalent to about 1,000,000 foot-pounds of energy striking the material as it goes in.
With each blow, the hammers pulverize the metal until it's small enough to fall through 6 square-inch grade holes.
It'll take a whole bus through the unit. It'll break it down in 7 to 10 seconds, densifies, fragmentizes, and comes out about the size of your hand.
In a single hour, the shredder tears through as much as 300 tons of steel, enough for 150 new cars. But the metal-on-metal friction inside can raise temperatures to over 400 degrees. So to prevent dust and other particles from igniting, over 40 gallons of water are pumped in every minute.
very destructive piece of machinery.
Once the metal's crushed, it's rolled beneath two powerful magnets that separate the iron-bearing material from other debris. Then it's ready to be melted down and reused all over again.
Just when you think you've seen it all, it keeps coming in.
Best of all, recycling saves an amazing amount of energy. To make new steel from raw taconite takes 4 times as much energy as it does to recycle.
Steel takes tons of energy to produce.
The energy saved by recycling currently reduces the annual energy consumption of the steel industry by about 75%, enough to power 18 million homes for a year. Steel plate. Thick, hard, heavy. At first glance, it doesn't seem like the ideal building material for a ship. But under pressure, steel reveals amazing abilities that make it the ideal material for building the next generation of American warships.
Steel is the heart and soul of these vessels.
So how does steel do it? How does a 1/2-inch thick rectangle of steel become the sharp curve of a destroyer? The answer is in steel's incredible malleability, which means that this tough and durable plate can be bent and rolled and shaped to the perfect specifications.
Putting ships to sea is one of the harshest environments known to man. And the strength of steel, the durability of steel, allows us to build these fine vessels.
Man, it's hot up in here.
Oh, welcome to the Mississippi Gulf Coast.
The work of creating these fighting ships of steel takes place here at the Northrop Grumman Shipyard in Pascagoula, Mississippi. Iron was first used to build ships in the 1840s. It wasn't until the end of the century that steel became inexpensive enough to use. But steel and its construction techniques weren't nearly as advanced as what they use here now. At Northrop Grumman, the shipyard workers start with plates of high-yield steel weighing 20.4 pounds per square foot.
It's all good steel. We don't use any cheap stuff in these boats.
High yield is an alloy that's infused with trace amounts of chromium, molybdenum, and nickel. This gives it an incredible malleability without sacrificing strength.
In ship construction, the high-yield 80 and 100 material are amongst the most advanced and desirable materials for this purpose.
In fact, this incredible alloy can absorb up to 100,000 pounds per square inch of pressure. Some mechanical engineers even speculate that if the Titanic were made of high-yield steel, it would not have sunk. Cutting these 3/8 to 1/2-inch thick sheets takes the ultimate tool, the plasma cutter. Plasma is an ionized gas, the same as the gases on the surface of the sun. This machine uses a powerful electric current to transform a jet of inert gas into a 30,000 degree Fahrenheit plasma cutting flame. Each specially cut steel slab has to take its turn inside a 2,700-ton roll press.
It's an art, okay? There's a lot of science involved as far as the pressure and the movement of the machine.
As the panel rolls through the press, pressure and heat are applied to bend the sheet to the exact specifications of the ship's curved hull.
After we roll across it a couple more times, it ought to soften up.
As you apply the pressure to the plate and it's rolled through the machine, you're transferring that pressure all the way across the plate.
Steel's ability to flex and bend without shattering is essential for surviving extreme ocean forces. Unlike its hull, the ship's deck must be perfectly flat and capable of bearing the weight of up to 5,000 personnel, plus aircraft and equipment. So during construction, it all comes down to the quality of the weld on the edges of the plates. To make sure the deck plates securely bond to the hull, the plate's edges must be milled down. Just like roughing up a surface before using glue, this treatment creates rough surfaces on both edges that anchor the newly formed weld.
The milling is done by a head that is put into this piece of equipment. It's got several teeth in each head, and as a piece of steel goes down the line, it just mills it as it goes.
Composed of 1% carbon and reinforced with tungsten for high heat applications, this incredibly hard steel alloy can cut through 750 inches of steel per minute.
It's pretty awesome to come in and see this in process.
With the edges prepped, it's time for the weld. With most materials, any kind of joint is a weakness. But because steel can melt and then solidify again, a weld is virtually as strong as the original piece itself.
Welding is a way of joining materials without having to use fasteners. But what you really are doing is you're locally melting the material, letting it flow together, solidify, as if you just cast it in place.
The ship's going up and down on the seat. It's twisting and turning. If we didn't weld the ship together, it would tear apart.
Today, assembling a destroyer from bow to stern takes almost as much time as the U.S. Navy spent fighting during World War II.
From the time that we unload the steel from the rail car, cut it, process it, build it, deliver this ship, is approximately 3 years.
But none of this explains how a ship made from solid steel panels can float. Despite the density and weight of each panel, the hull is wrapped around an essentially hollow inner core, so the volume of the water displaced by the ship weighs more than the steel in the ship.
What we really have to look at is the old Archimedes principle that you're displacing an amount of water, and that provides a force that holds things up.
Thus, steel floats. It saves lives, flies over water, and floats on top of it. It was one of man's great technological breakthroughs, and it still ensures the nation's security. And best of all, it's recyclable. So even as the world's iron ore reserves begin to dwindle, there should always be a ready supply of the world's ultimate material, steel.